Alright, test review. Who first theorized about atoms? Who first thought about atoms? Who, yeah, who introduced atomic theory to the world? Mm-hmm. So what did John Dalton do? He took lots of experimental data and came to the conclusion that atoms existed and compounds were combinations of atoms. Each compound had specific atoms. Each atom was unique and had its own properties. Who discovered the electron? How did he discover it? He sent current through a cathode ray tube.
Cathode ray tube.
See if I can find a picture of it. So here's one common example of a cathode ray tube. It's a glass tube. You have a cathode, an anode, run electricity through it or put a voltage difference. Electricity is going to fly through it, stripping the electrons off and creating light as new electrons fall back down. His experiment was more like this. So here's a cathode, and we have a piece of paper that can detect more easily electrons, so it glows or fluoresces whenever electrons fall onto it. So he has the way to detect negative particles or charges. And you notice that there was no charges in here to begin with, and when electricity runs through it, charges start appearing. Basic schematic of it. They have a fluorescent screen that glows in the presence of charges, negative charges, and basically he generates electrons here. These two help steer it into a single beam, so more precise than just having electrons flow randomly, and was able to see electrons being hitting the screen. What was this model called? That would be the plum pudding model. So atom was filled with a positive fluid or substance with electrons scattered like raisins. A cathode ray tube is just a tube filled with a neutral gas. That allows you to connect it up to electricity. Who discovered the atom had a nucleus? positively charged nucleus. This would be Ernest Rutherford. How? Shot alpha particles at gold foil and saw them scatter and saw them bounce backward. Who discovered the neutron? How? So remember I said this was a mistake. I said first it was isotopes, but I said later it was because of alpha particles. So you notice alpha particles hitting wax produce both protons and neutral particles. The neutral particle traveled the same distance as protons, so must have had the same mass as protons. Letting me go back. What is the Bohr model? The electrons orbit around nucleus at specific energy levels. What did de Broglie do? I've mentioned it. I haven't written anything in words, but he discovered the wave nature of electrons. He still thought they were particles, but moved in a wave-like motion. So here, for example, you can see the wave. So this image on the right is a traditional wave. So instead of it being circles, he thought that they made so many wavelengths around the atom. So, for example, on the right, this would not be a possible orbit because the connections don't line up. The one on the left would be a true orbit because the wave connects back in itself. So he figured that the reason why they have certain energy levels was because they had to complete so many wavelengths. You can see here there's a mismatch right here slightly, so that wouldn't be a true. But if we look at it, instead of them going in orbit, circular orbits, they go in this wave pattern. So the wave is, let me look up transverse wave. So a transverse wave looks like this. This is your traditional sine. And he theorized that they wrap around, and this is how the electrons move. And then they produce these standing waves. So they don't have to they can go in multiple ways. But basically, the electron had to follow this pattern. So here's another example. So he laid the foundation for the next theory. So again, the one on the right, another way of looking at it. Basically, explain why they could only exist in certain energy levels. So the Bohr model just randomly stated these electrons are going to be at certain energy levels. I have no clue why, but every time we look, they're in certain energy levels. De Broglie figured out an explanation. Now this explanation has turned out to be wrong. There are some people who still support the Broglie wave mechanics and quantum mechanics. There's some problems with his interpretation of quantum mechanics. Quantum mechanics is weird, and so for every attempt to describe a proton or electron as actually existing as a particle has failed. The number one attempt is still the Copenhagen interpretation. There is no electron. You just have a cloud of probability. This cloud of probability Every time we look, it collapses and the electron appears in one random spot. Which brings us to the last model, the electron cloud model. Who came up with it? Yes. So this would be Erwin Schrödinger. Electrons don't have definite positions. Instead, we can only describe probabilistic location. So, not a very good one. So if we were to continually look for the electron, we keep finding it in random places. If we put a spot on where the last place we looked at it, it'll generate this pattern. Pattern is the probable location or the cloud. The more dense it is, the higher we get. But if we just keep track of every location we found it, we notice it's all random. What's an isotope? How would you describe it? That's not a real good. An atom that has what? Same number, or I should say, atoms that have the same number of protons, but different number of neutrons. What does this number represent? And what is it equal to? Protons plus neutrons. What is this number? That's the number of protons. And what is this? The element symbol. There's also the element hyphen mass number. Notation. So this is known as a hyphen notation. This is hyphen notation. This is symbol notation. Also, we call it isotope notation. Technically, these are both isotope notations. But I might give you one or the other and ask you how many protons, how many neutrons, or how many electrons. And remember, unless otherwise stated, atoms are neutral. What does neutral mean? Neutral means no charge or protons equal electrons. What's the charge of a proton? Plus 1, positive. Charge of electron, negative 1 or negative. Charge of neutron, 0 or neutral. For assumptions on mass, is proton is 1 AMU, neutron is 1 AMU, An electron is 0 AMU. In actuality, neutron is ever so slightly more massive than a proton. But we will be keeping with the assumptions. There's a question where I will accept whether or not you use the assumptions or use this. Because you can argue both cases. There will be some nuclear balancing. And did everyone finish the homework and turn it in? So there'll be a few balancing equations like that homework. Me asking whether or not the equation is a fission or fusion. Looking at the periodic table, what is the most common isotope of carbon? So, carbon 12 or carbon 12? So you round this to the nearest whole number. I might add to the test average atomic mass. So, it's just how we do weighted averages. So if I say that 70% of an atom has a mass of 10 AMUs, and 25% has 11 AMUs, and 5% has 12 AMUs, you just do the weighted average. Two ways of doing it. You can do 10 times 70% plus 11 times 25% plus 12 times 5%. And to get rid of the percent sign, you would divide by 100%. Or you can realize that you could just multiply directly 70% times 10, 25% times 11, and 5% times 12, and add them together. Depends on what you're more comfortable thinking of. In higher level mathematics, you should recognize that 70% is the same thing as 0.7, and 25% is equal to 0.25, and 5% is 0.05, but it probably makes it easier for you guys to just do it like this. And what would be the mass of carbon-12? Yeah. So using our mass assumptions, the mass number is the mass. So our assumptions on mass number equals mass of isotope. We're slightly wrong due to binding energies causing the protons to, or causing the nucleus to gain additional energies. Currently, I don't have a question on there, but I'm probably going to add it. I need to see how many questions, or how many points each question is worth. See if I can squeeze it in. I wanted to also go over half-life, but I didn't. I'm still going to teach it right now, but this isn't going to be on the test. So there are two categories for isotopes: unstable and stable. Unstable means the isotopes will continuously and spontaneously break down and decay into lower atomic weight. Stable means that they do not naturally decay and can exist in natural materials. Radioactivity means the process by which a nuclei spontaneously undergo a transformation to other isotopes with the corresponding release of radiation. So if it's unstable, it will eventually break apart. Half-life is a measure of radioactivity, or how radioactive something else is. So half-life, and this won't be on the test, but I wanted to teach it. Half-life is the time it takes for half of the substance to decay. So, for example, let's say we started out with 8 grams of a radioactive material that has a half-life of 24 hours. So 1 day. So day 0, when we first begin, we have 8 grams. 24 hours later, and this is random, but statistically, we'd have 4 grams left. We lost half, so half-life is the time it takes for half of it to decay. Day 2, we would have 2 grams. 24 hours later, we'd have 1 gram. 24 hours after that, we'd have half a gram. 24 hours after that, we'd have a quarter of a gram. So how many grams would we have after a year? So let's see if we can generalize this. So I'm multiplying by a half to get from here to here. To get from here to day 2, I multiply by a fourth. To get to day 3, I'm multiplying by, what would that be, an 8? Does anyone know of another way to write an 8? 1 over 2 to the third power, where this corresponds to the day. So you can rewrite this as starting amount times 2 to the negative days. I don't know if you know this, but 2 to the negative power is 1/2, or 5 to the negative 1 is just 1/5. And if I do 5 to the negative 2, that's the same thing as 1 over 5 squared. So the negative just means flips it over. So if you wanted to figure out how much would be left in after 356 days, so that would be, we start out with 8 grams, 2 raised to the negative 356. It basically, there wouldn't be any left. Let's see, where would nanograms be? 180 days? So after 30 days, we'd be in the nanograms. So, to give you an idea, half-life of common radioactive isotopes. I want in years. Where's it all? Let me give you all some ideas, some comments. No, it doesn't. I mean, you could do it as, I mean, this is equal to starting amount divided by 2 to the days. That way you did use division. What? Did you use division? If you remove the negative, you're going to get a positive number. Last time we got E negative 101. Or 103. Oh, yeah, okay. Yes, you can use a half. Because 2 over 5 squared, that's the same thing as 2 squared over 5 squared. So if you did 1/2 raised to an x, that's the same thing as 1 over 2x. Or you could put it as 2 negative x. So I want to give y'all some ideas of some radioactive stuff. So carbon-14, this is what we use to do radioactive dating with. So how carbon-14 works is radiation from the sun strikes CO2 in the air. Or how does carbon-14 form? It's so nitrogen. Energy from the sun hits the nitrogen in the air, causing it to break apart, releasing a neutron, which turns nitrogen. So neutrons with nitrogen-14. So cosmic rays hitting the air hits nitrogen-14, which eventually produces carbon-14. and we breathe it in because it's constantly being produced in the air. We absorb carbon-14 radioactive isotope into our bodies. It's not that radioactive, so it doesn't hurt us. But when we die, we stop breathing. And so everything that breathes in material, a certain portion of all the carbon atoms are going to be carbon-14. After 5,730 years, half of all the carbon-14 in your body and your deceased bones and stuff will decay away. And another 5,730, another half will disappear. So the remaining half will half again. And we can look at the percentage of carbon-14 to carbon-12 in your body. And depending on, we know the baseline. We know living things have a certain percentage, and we can look at how that percentage drops. Uranium-238 is very safe to handle, actually. I could have a block of uranium-238 on my desk and play with it. You don't want to eat it because of metal toxicity or do anything like that. But it's 4 billion years, 4.5 billion years. What decays into is very another thing is potassium. One banana actually has a good percentage of radioactive potassium. It's actually a unit of radiation. It's called a banana. What is it called? I ran out of time. It doesn't have it. This is the most dangerous one in the house. Radium. 1,600 years. And no, radon. 3.8 days is released from Earth's crust, and people have died from radiation poisoning, and especially in their basements. So that's it. Test will tomorrow.